VB theory is most useful for describing reactions and bond dissociations. Important chemical concepts such as resonance are based on VB concepts. Let us look at the glossary. We will be studying about valence bond theory and we will also be studying about hybridization. Before we start at valence bond theory, we will just recap what we have studied earlier. Before we start looking at VB theory, we will just recap what we know already. When we talk about bond formation based on atomic interactions, we use the potential energy diagram as shown. This is for the hydrogen molecule. This is the potential energy diagram for hydrogen molecule. When the internuclear distance is 250 picometers and above, that is close to 275 picometers as shown here, there is a large separation between the hydrogen atoms and there is no interaction, rather we will say there is no attraction. So in the previous modules we have studied about for forming a bond, we do need attractive interaction between the interacting atoms. So here, since they are having large distance between them, there is literally no attractions between the hydrogen atoms. When the atoms approach closer as shown here, when the distance is around 150 picometers, there is a small overlap. That means there is a small attraction is happening between the two hydrogen atoms. And when they reach the maximum, but at 74 picometers, the covalent radius of hydrogen, there is a maximum attraction leading to the lowest energy. What we have seen from this potential energy diagram is minus 103 kilocalories per mole. In other words, there is a maximum attraction leading to the lowest energy for this particular arrangement. And when the atoms comes any further, that leads to instability and the potential energy of the molecule increases. As we can see here, when the distance is around 50 picometers, there is a large repulsion between these two atoms. That is the reason the potential energy increases very high. This is because of the repulsion that exists between these two atoms. Now, in this module, let us ask the simple question, why we need to study about VB theory or say MO theory. In this and the couple of next few modules, we will find the reasons. In the last module, we have studied about VSEPR theory and we also know there were few limitations with respect to the VSEPR theory. For example, geometry of water molecules could not be explained by the VSEPR theory. And in the case of single bonds, the different bond energies, say for example, if you look at hydrogen, it is 104 kilocalories per mole, fluorine, it is minus 36 kilocalories per mole, and the bond length for hydrogen is 148 picometers and fluorine 128 picometers. Because there is a huge variation in the bond energies as well as bond length between hydrogen and fluorine. This could not be explained by the VSEPR theory. So let us look at the importance of bonding theories, mainly the first one, which is the VB theory or the valence bond theory. Linus Pauling received Nobel Prize in 1954 for putting forward this valence bond theory, and Erwin Schrödinger received Nobel Prize in Physics in 1933 and Robert Mulligan received Nobel Prize in Chemistry in 1966 for putting forward the molecular orbital theory. So what is the similarities between VB and the MO approach, that means valence bond theory, and the molecular orbital theory approach? They both construct wave functions for the molecule. Both take different mathematical approaches, but their results are more or less similar. You have to remember one thing, when we talk about VB theory or MO theory, both of them use lots of mathematical calculations. So here we will be studying mainly the qualitative and conceptual ideas rather than mathematical and numerical calculations. In both the approaches, the wave nature of the electron is used for the calculations. The minion asks the question, why electrons are used and not the nucleus in these two approaches? This is actually explained by Born-Oppenheimer approximation. According to this, what we can say is nuclear and electron movements are basically separate, and electrons actually move very fast. Nucleus on the other hand does not move or move very slowly. So we can assume that the nucleus is fixed or the nuclear motion is nil when we consider how the bonding is formed. Let us look at the valence bond approach. So this can be derived from the simple Lewis structures. It uses basically overlap of atomic orbitals, and overlapping leads to bonding, and this overlap happens within a confined region. That means it is basically a localized one, and the mixing of these orbitals actually leads to hybridization. These hybridized orbitals are degenerate in energy. That means all the hybridized orbital will have same energy. When we say sigma bonds, these are hybridized orbitals, basically sp3, sp2 or sp orbitals. When they hybridize leads to sigma bonds. When we say pi bonds, these are from the overlap of unhybridized orbitals, mainly p orbitals. This is basically not a physical phenomenon. In other words, hybridization does not happen by mixing of physical orbitals. Basically, it is only a mathematical representation, and the electron density of an isolated free atom is not disturbed. So these are all some of the assumptions while we create the VB approach. And why we have to follow this VB approach? We will just look at some of the advantages. The first one is it is very easy to understand. Then it actually provides a method of describing the shape, that is the geometry of the molecule, but it does not predict
the shape of the molecule.
When we say overlap of orbitals, what is the overlap of orbitals? We will look at later part. And the VB theory is extremely good at explaining how the reactions actually proceeds. And this also explains the bond dissociations in various molecules. And the most important thing is VB theory can explain the resonance phenomenon which was observed in various organic molecules. So these are all the various advantages of the VB theory. That's the reason people had been using VB theory for explaining the shape of the molecule. Now we have seen about the VB theory. Let us look at what is hybridization. Why we have to study hybridization and how the hybridization actually occurs. So these are all some of the questions we will be answering in this session and in the next couple of sessions. So what is hybridization? This is basically overlap of atomic orbitals. This leads to different geometry. That is, this basically influences the molecular geometry and bonding properties of the molecules. The resulting hybridized orbitals will have different energy than the mixing orbital. So this is the major difference before hybridization and after hybridization. So how the atomic orbitals change. So this is what is explained by the hybridization concept. The number of atomic orbitals mixing will be equal to the number of hybridized orbitals. So this is the major thing we have to. The number of atomic orbitals mixing will be equal to the number of resulting hybridized orbital. So this is about what is hybridization. Why we need hybridization? Let us answer this question. The concept of hybridization was introduced to provide a mechanism for achieving the directionality in bonding. So when the bonds are formed, how the directionality occurs is explained by the hybridization. Say for example, if you look at the methane molecule, it is actually having a tetrahedral shape. So how the tetrahedral shape is formed is explained, that is the directionality of the bonding is explained by hybridization concept. And to explain the linear geometry, so that means basically the geometry is the most important observed phenomena. To explain the observed phenomena, hybridization concept was invoked. In other words, the linear geometry compounds can be explained by the sp hybridization. The trigonal planar geometry of compounds can be explained by sp2 hybridization. Say for example, when we talk about carbocations, they are planar in nature. So those planar nature can be explained by the sp2 hybridization concept. And when we talk about tetrahedral geometry, sp3 hybridization was introduced to explain the bonding in molecules like methane, which are having tetrahedral geometry. So one thing you have to keep in mind, that is, hybridization does not lead to geometry, but to explain the geometry we use hybridization. Let us look at little bit more details about hybridization. We have given some general molecular formulas here, AB2, AB3, AB4, AB5, AB6. There are two variants, and what is the hybrid set also we had given here. If you look at the AB2 type molecules, they are formed by the sp type hybridization. So that was written here, sp type hybridization. The s and p character of the resulting hybridized orbital will have 50% s character and 50% p character. That means 1:1 ratio of mixing is seen in this type of molecules, and the bond angle observed is 180 degree. In other words, we can say the linear geometry is the one what is available for this AB2 type molecules. Some examples include BeCl2, or even in organic chemistry we have compounds like alkyne are having sp hybridization. So to explain the linear structure of the molecule, we use sp hybridization. And the next one is for AB3 type molecules, we have sp2 hybridization. So here the S character is 33% and P character is 67%, and the bond angle is 120 degree. So the geometry of these compounds are basically trigonal planar. In other words, whenever we have a trigonal planar molecules like alkenes or BF3, we use sp2 hybridization to explain their geometry. And the next one is sp3 hybridization, which is very common for many organic compounds. So here we have 25% of s orbital contribution and 75% of p orbital contribution in the sp3 hybridized orbitals. The bond angle is 109 degree 5 minutes, and tetrahedral shapes could be explained by the sp3 hybridization. So an example given here is methane molecule, especially alkanes are having this sp3 hybridization. And many other inorganic compounds can also be explained by the hybridization concept. sp3d hybridization could be used to explain trigonal bipyramidal structures like PF5 molecules. In the case of octahedral complexes like molybdenum hexacarbonyls, we have D2sp3 hybridization, and for SF6 we have sp3d2 hybridization. So these are various types of hybridization which are available to explain the different geometry of the molecules.